Yeah, hello everybody. My name is Morio. I'm a doctoral researcher at the CISPA Helmholtz Center for Information Security. And in today's talk, I will present you the results on the automated analysis of exposure notification systems, which is joint work with Ilkan Esiyok, Dennis Jackson, and Robert Künnemann. It all started in December 2019 when a mysterious illness was discovered in China, slowly spreading and quickly spreading across the world. In the case of disease outbreaks like the coronavirus, contact tracing is an important public health tool for slowing the spread of the virus. Contact tracing is a process of identifying people who have been in contact with persons that have been infected by the disease, such that they can take the appropriate measurements like self-isolating and social distancing. To simplify and accelerate the process of notifying people, digital exposure notification systems have been developed, making use of the ubiquity of mobile phones such that they can be deployed easily and scale fast. The aim of an exposure notification system is to notify people who may have been exposed to disease by being in contact with an infected person. In this work, we answer the following research questions. First, we try to formalize the different security properties of exposure notification systems. Then we look what attacks are possible for the systems. And thirdly, we check what the maximum impact of these attacks is. We focus on three popular exposure notification systems, starting with a robust and privacy-preserving proximity tracing protocol, short ROBOT, developed by the Privatics team at INRIA and Fraunhofer ISAC. This is a protocol that is used by the French 2 anti-COVID app, which has now more than 60 million downloads. Second, we look at the original proposal of the decentralized privacy-preserving proximity tracing protocol, short DP3T, developed by Trancoso et al., and which influenced the development and design of the Apple-Google exposure notification system. And finally, we look at the implementation of the German Corona-Warn app, developed by SAP and the Deutsche Telekom, which has now more than 48 million downloads. And if you take all the compatible applications in the European Federated Gateway Service, which is a system for cross-border contact tracing applications, then we have more than 208 million downloads, which shows that the applications has achieved the right range of adoption. And we perform our analysis and formal models in the Tamarin Prover state-of-the-art protocol verification tool. To highlight and get a better understanding of how these approaches work, let us contrast the robot protocol in the centralized setting with the decentralized protocol DP3T. In the case of robot, we first start with the registration phase. We have a phone and we have a backend, and both exchange keys, and the backend also stores the identity of a phone. Now, the backend also sends a batch of so-called ephemeral messages to the phone, which contain metadata and also the identity of each phone, and is encrypted by the backend secret key and the just exchange key pair. When this phone now comes into contact with other applications also using the same protocol, they exchange these ephemeral messages over the Bluetooth communication protocol. Each phone stores the messages they receive from the other phones. Now, if a user doesn't feel well and performs a test at a health authority, then if this test gets positive, they get an authorization code. And with this authorization code, they are now able to upload their keys, their ephemeral messages, to the backend. As the backend already knows all the relevant keys for decrypting these messages, and the backend does so and gets the identities of all the persons in these messages, namely the contacts of the infected person. The backend can then compute a risk score and sends this risk score to the other persons to notify them that they may have been in contact with COVID. We call this a centralized setting, as here the risk computation is completely done on the backend. In contrast, in DP3T, we don't have any registration phase. Each phone generates freshly daily keys and keeps a list of the last 14 days of keys. If this phone now comes in contact with other phones using the same approach, they again change ephemeral messages. These are now generated by the phones themselves and contain also metadata, and each phone stores a list of the received messages. Similar to robot, we can now perform a test. If this test turns out to be positive, we can again request an authorization code. And with this authorization code, we can again upload our data, but here the crucial difference is that we upload the last 14 days of daily keys. And here the backend only serves as a distribution platform for these daily keys, and each phone downloads these keys in a regular interval, uses these keys to try to decrypt the messages they received from the other peers, and by this they get enough information for computing a risk score and then show the user the relevant notification. This is a decentralized setting, as here the backend only serves as a distribution platform for the keys, and the phone perform the risk computation on their own device. Now we are interested in the security properties of exposure notification systems. We look at two security properties which have been previously formulated but only informally, and we are now trying to formalize them rigorously. One of them is soundness. So soundness has both space and time dimensions. We assume that at some point we have a risk notification on a phone, and then soundness requires us that at some point T we met with an affected person, and this contact occurred in the contiguous period of the phone as determined by a health authority, which is normally less than 14 days. If this holds, we say soundness holds. And we formalize this as a trace property in the Tamarin prover. Another security property is upload authorization. Here we assume that we have a backend that already accepted the upload of ephemeral messages, like in the case of Robot, or the upload of daily keys in the case of DB3T and the CWA. Then there exists some phone which either received these messages or generated these keys, and in between we tested positive. So in general, we assume only that positively tested phones can upload their data to the backend. And again, we formalize this as a trace property in the Tamarin prover. So now we are interested in the attacks against these two properties. Let us first come to our attack model. Our attack model offers a wide variability of capabilities for the attacker, like the injection, reading, and also editing of messages on the Bluetooth communication channel and also the internet communication. The attacker can be at multiple locations at the same time, and they can also compromise any number of agents. They can compromise backend, the health authorities, and any number of phones. And now with this in mind, we are now trying to derive the possible attack scenarios for the attacker. A priori, we assume that the attacker can do everything I just described, but now we are basically asking the question, what does the attacker actually do? For example, we want to we want to get all the attacks against soundness. Then we try to prove it, and Tamarin provides us with an attack trace directly categorizing the attacker's behavior. The number of agents they compromised, their interaction between the other agents, and everything else. We can use this to extract an attack pattern and the attacker's behavior in another property, P1. And then again, we now have a new property, either soundness holds or the attacker behaves as P1. We can again try to prove this property. If this is holds, we have found all the attacks that are possible against soundness. Otherwise, we get another attack trace, can extract another attack pattern, so on until we found all of the different attack patterns against soundness. This is a very flexible approach, and we don't have to limit our threat model a priori and can evolve dynamically. We also perform the same approach for upload authorization and get in total 27 attack patterns, 18 for soundness, 9 for upload authorization among the 3 different protocols. Now we are also interested in what is the maximum impact of these attacks on the system. Here in this situation now, the attacker tries to cause false risk notifications. That is, they try to break soundness and sending out notifications to people who didn't actually have been in contact with any infected person. So they try to disrupt the system, and here this attacker acts as a group of individuals. I want to highlight 2 interesting scenarios here, which separates the centralized from the decentralized model. In the case where the backend is corrupted in Robot, basically everything is lost. If the attacker can control the backend, they can send risk notifications for any registered phone, and there's no other agents involved. In the case of DB3T or Robot, we at least have require some form of Bluetooth communication that has to happen such that we can provoke false risk notifications. Another interesting setting is if we have an infected phone that is a phone and we have an authorization key that allows us to upload our data at some point. If you now want to provoke risk notifications in the case of Robot, we can simply gather all the ephemeral messages from other people. For example, we can also scale this attack dramatically by using a passive antenna and install it in some location which is frequently visited, like a public train station, gather all the ephemeral messages, and then upload it with one key, causing a lot of risk notifications for people that haven't been actually in contact with the person. A similar attack is also possible in the case of DP3T and CWA, but here instead we need an active antenna to send out our ephemeral messages, such when we upload our daily keys, they get the corresponding notification. So in conclusion, we provided 3 formal models for common exposure notification systems, the robot protocol, DP3T, and the CWA. We provided a complex spatial and temporal interaction between the agents and also allowed a fine-grained attack patterns which allow us to make quantitative assessments about the different attacks. In total, we found 27 attack patterns, which is also currently pushing the limits of existing tools, both on the computational side and also on the modeling side. We provide a systematic categorization of the different attacks or of new and existing attacks, which allows us to get a better understanding of the requirements and consequences of the attacks. And as a takeaway message, in general, we say that it is possible that a knowledgeable attacker can mount an attack on these systems with a low risk of identification. So that concludes my talk. Thank you for your attention. You can find our models on the GitHub link. I'm happy to answer your questions.